Okay.
Problem, huh? Still.
Yeah, sure.
Mhm. Yeah, if there is any issue in the middle. Yeah. Okay. Good evening, everyone. I welcome you all to the final day, final event of the Career Leave Days, fifth Career Leave Days. Today, we have Professor Deepjyoti Goswami. He is an assistant professor at Department of Mathematical Sciences, Tejpur University, Assam. He will be talking today about on the completeness property of R. He has got his PhD from Indian Institute of Technology, Bombay in 2011. After that, he has been a research associate at IIT Bombay and followed by postdoctoral position at UFPR, Brazil. Uh, his areas of research interests include elliptic and parabolic PDEs, Navier-Stokes equations, finite element method, and many more. We are glad to have you, sir. Welcome to the Career Days. Over to you.
Thank you, Chaitanya, for the introduction. And good evening, all. So, yeah, so today's topic is on the completeness property of R. I have packed a lot of stuff over here in 1 hour. So I'll quickly go through the initial part, assuming all of us are familiar with this stuff. So in our very first class, we usually hear that R is a complete ordered field. And we are interested in this completeness property of R with different facets. So by R, we mean real numbers, or one can think of the real line. As I was saying, there are some algebraic properties, which are field properties, assume order properties. Our interest is in completeness property. That's that a real number, set of real number is complete in more than one sense. Let's begin. We'll assume that our sets or subsets will be non-empty. And by upper bound, I mean there's a real number u for a set A such that u is greater than or equal to all the elements of the A. And in that case, we simply say that A is bounded above. It's quite interesting to see that if u is upper bound of a set, then anything greater than u is also an upper bound. So there's no point looking at the right of u. Can you look at the left of u? Obviously, a smaller upper bound or possibly a smallest or least upper bound. That's what is completeness axiom or least upper bound axiom, which says that any non-empty subset of R with an upper bound has a least upper bound, or any non-empty bounded above set of R has a least upper bound. We are saying it here as axiom and not property because when we start with this, we do not prove this statement. We prove everything else, but we never prove this. So that's why we start saying that it's an axiom. But later on, we'll simply mean that least upper bound property. And we are quite familiar with this, I'm pretty sure. So what do I mean by least upper bound of a set? So given a non-empty subset of R, a least upper bound or supremum obviously first itself is an upper bound, and it is least among all the upper bounds. That means if beta is any other upper bound, beta has to be greater than or equal to alpha. Standard notation of supremum is LUB of A, supremum for A, or sup of A. And anything less than alpha, the supremum is not an upper bound. That's by definition. That means if B is strictly less than alpha, then we must have an element of A that is strictly greater than A less than equal to alpha. And one can easily show that if supremum exists, it is unique. Characterization of the supremum. This is very useful. we have already seen that anything less than supremum is no longer an upper bound. So if we start with a supremum, alpha is the supremum, then anyway it's an upper bound. Also, anything less than that supremum, alpha minus epsilon is less than alpha. So that means it's no longer an upper bound. So there must exist an element A which is strictly greater than this. We'll keep this in mind that whenever alpha is the supremum, alpha minus epsilon is not an upper bound for every epsilon, and so we'll find an element A greater than alpha minus epsilon. Okay, this will be useful. Some observation. If A is bounded above, then negative of the set, that means all the elements, negative elements A, where A belongs to A, would be bounded below. Geometrically, it's very easy to see. If you imagine that A is on the right hand side of the origin, just imagine A is on the right hand side of the origin on the real line, then negative of A would be on the left hand side of the origin. So it can be thought of as a mirror image. You put a mirror on origin, you get a reflection. And if A is bounded above, minus A is bounded below. So a bounded below set means I can talk about lower bound and greatest lower bound or infimum. In fact, it is easy to verify that if alpha is a supremum of A, then minus alpha is infimum of minus A. So in fact, very existence of supremum also guarantees the existence of infimum. We can put it as a property, greatest lower bound property, that every bounded below set has a greatest lower bound. That means there exists a B, beta, which is a lower bound, and it is greatest among all the other lower bounds. If you have any other lower bound, then beta must be greater than or equal to. So it is the greatest lower bound. And as we have mentioned, it is equivalent. It is very easy, almost straightforward to prove that if we assume existence of supremum, completeness axiom of R, then it is easy to prove greatest lower bound property and vice versa. So we'll not spend time over here. Just by assuming there is a supremum, this completeness property of R, we have some immediate application. For example, Archimedean property of R, that if you take two real numbers, both positive, then there exists a natural number n such that nx is strictly greater than y. One can say that y need not be positive. Yes, y need not be positive, but that is redundant because you already assume that n and x are positive. So any zero or negative number would anyway be less than nx. Also, if I assume x equals to 1, it simply says that n is strictly greater than y. That means set of natural number is not bounded above. If you give me any real number y, I can always manage to find a natural number n such that n is strictly greater than y. It's an immediate result of existence of supremum. For example, if you assume this is not true, nx is not strictly greater than y, then it must be that nx is strictly less than equal to y for all n. And then this set is bounded above. That means it should have a supremum. Anything less than that supremum is no longer an upper bound. I must have an element from A. And this simply says that alpha is strictly less than nx plus x. Plus n plus 1x is an element of A. So alpha is no longer an upper bound, so it has to be a contradiction. Okay, so you have seen it in init math, I believe. And as a consequence of this, we can say that rationals are dense. So I'll be skipping this, but one can obviously check that irrationals are also dense in R. And between any two distinct reals, there are infinitely many rationals and irrationals. So these are some very useful results that comes immediately. One can also check that least upper bound axiom holds in Z, that is in integers, but not in Q rationals. So these are preliminary stuff. So here comes the first word, NIP. Although I believe you have seen this nested interval property. So when we talk about completeness property of R, we talk about a bounded set and some property of the bounded set. For example, it has a supremum. So it's basically a property of sets, bounded sets. So can this property be seen from some other angle? So here is the first case, nested interval property. So we consider nested sequence of closed bounded non-empty intervals. And it says that this intersection is non-empty. Okay, so let's try to have a look what we are trying to say. So we'll try to prove geometrically most of the time because we have limited time. So assume that this is your I1 first. This is your I2. This is your I3. And so on. So these are my AIs, A2, A1, A3, and these are my B. You can observe that if I consider A to be the collection of these AIs or ANs and B to be the collection, then this set of AIs, these are bounded above by BIs. Each BIs are actually upper bound. So it has a supremum. It has a supremum. We call it ASA. And similarly, all those BIs are bounded below by AIs. So I have an infimum, call it P. I'd like to claim this. So what I have initially, I'd like to claim that somewhere here between ANs, each AN and BN, this AB resides. Okay, so I don't know. This is becoming so A and B somewhere here. So sorry about this. I don't know what's happening. This becomes too sensitive. Well, so observe that, and B is this. So from the previous picture, we can say that A is greater than equal to all AIs. So A lies where somewhere here, but BIs are already upper bound. BIs are already upper bound, so A must be less than or equal to BIs because A is supremum. Similarly, BIs are infimum of this. So BIs are anyway in the left of this BIs, but AIs are also lower bound of this BIs. This is the greatest lower bound, so it has to be on the right, bigger than all that. So A and B actually lies in between A and B. And in fact, A and B lies in between all of AN and BN. So from here, we can complete this A. This is one thing that we need to prove, and we can prove it in fact. We will not spend time, we can easily prove that in fact A is less than equal to B. With this understanding, it is sufficient for us. What I intended, even if I assume that only A is there or AB both are there, I do not need which one is bigger than which. Because what we have proved, if A and B lies in between ANs and BNs, it simply means A belongs to all of the INs intervals, B belongs to all of the INs, and hence intersection of ion is non-empty. Okay, so I do not know what is happening over here. So A, B in fact belongs to intersection of these ions, and hence this is non-empty. We can go one more step with a statement of NIP that it in fact this is equal to this closed interval AB first of all. And second of all, if we assume that length of ions are going to 0, it simply implies that Bn minus An goes to 0 as n goes to infinity. So remember, A and B are sandwiched between A and B. A and B, A, B are in between A and B. So we can intuitively, at least, we can easily show also that A equals to B. So that means if length of ions goes to 0, we can show that this intersection is in fact singleton. Okay, so what we have shown is nested interval property. First of all, if we have nested sequence of closed bounded non-empty intervals, their intersection is non-empty, and we can show something more. In fact, what we have shown, if this intersection is not only non-empty, we can define what it is. And moreover, if length of the intervals are going to 0, and there's a mistake, this intersection is singleton A. This is not element, it should be a set with curly brackets. Okay, it will be singleton A. So we have established nested interval property by means of completeness property. We want to show that if we assume nested interval property, we can show the completeness property of R, that means LUB property. So that's what we propose. Okay, so what we have to show, that any non-empty bounded above subset of R has a least upper bound. So again, let's go back here. So I have NIP basically, and I have to show LUB property. What LUB property says, if you have a non-empty bounded subset of R, A bounded, then sup A exists, right? Sup A exists. So let's look at graphically. We'll quickly try to prove it graphically. First of all, A is bounded, right? So if A is bounded, it must be in between some interval, something like this. Okay. I want to show that it's supremum. Okay, I'll not. Okay, fine. Let's try. So my sequence are somewhere here. Okay, they're I assume that there are infinitely many. If range of the sequence is finite, this is okay. Sorry, what I'm using. Sorry, no, I'm not talking about sequence. I am so sorry. So let's go back here and try to understand from here. Any non-empty bounded above subset of R has a least upper bound. So what we have to show, I'll start with a non-empty bounded above subset. Let A be a non-empty bounded above subset, and I will try to show it has an upper bound. But what I'll be using? I'll be using nested interval property. That means I have to create some interval. How do I create an interval? That's the whole point. So I create an interval by taking, so A is a non-empty set, so I can take an element of A. This is an element of A. And I can take an upper bound. This is an upper bound. So this is an upper bound and this is an element. I can take this. Why this is possible? It is possible because A is non-empty. I can take an element and A is bounded above. So it's an upper bound. So now this is my first set I1. This is my first set I1. So in this set, I take a midpoint. Now this midpoint, if it's an upper bound, then I will consider this set. So let me repeat how I have considered my first closed interval. I1 is considered as starting with some element of A and some upper bound. Both exist, an element exists, A is non-empty, and upper bound exists because A is bounded. So that means I have an interval closed and bounded interval this. I considered a midpoint of it. Now this midpoint may be an upper bound. If it's an upper bound of the set A, then I consider this new set. If this is not an upper bound, if it's not an upper bound, meaning what? There should be element here. So that means now I'll consider this set. You understand the construction? From I1, I have constructed either this as I2 or this as I2. I2 is a subset of I1 and length of I2 is either equal to half or in this case less than half of length of I1. This is the whole idea. Okay, we'll proceed in this manner. So that's what I have said. A is non-empty, so I can choose an element A1. It is bounded above, so I can choose an upper bound. So that's I1 is a closed and bounded non-empty subset. I take a midpoint. Now this midpoint can be an upper bound. Then I will consider this subset. Otherwise, I will have an element greater than x1, so I will consider this subset. But in both cases, the subset I will call as A2, B2, which is a subset of A1, B1. And remember, A2 is still an element of A, B2 is an upper bound. And length of I2 is less than equal to length of I1. So if I, now again, I will take the midpoint of I2 and I will proceed in the same manner. I'll repeat. And we can use induction, mathematical induction, to show that I have a nested sequence of closed interval. Okay, they are non-empty, bounded, closed intervals. So now I am ready to use NIP. Since length of ions are decreasing by half or less, they are in fact going to 0, and NIP allows me that intersection is singleton. Say A. Singleton A. Again, there should be curly bracket. So this is the final step, that A is the least upper bound for A. Remember what we are looking for? We are looking for that every bounded above non-empty set has a least upper bound. And we got some element A. Pictorially, if we go back to the picture, A and are increasing elements of A, B and are decreasing an upper bound of A. So somehow intuitively, as if A and B are coming closer and closer to each other, and anything in between should serve as a least upper bound. Let's check. First, I have to check that A is an upper bound for A. So if not, I must have an element B belonging to A. Okay. So let's go back to the picture. If I see where I was, so observe that this is I1. My set is somewhere here, maybe scattered. I don't know, but it is somewhere here. I have picked some elements and then upper bound. So the way I'm picking elements, they are increasing, and the way I'm picking upper bound, they are decreasing. And what I have claimed, that in between there is something which I call supremum. So just imagine that initially I started why. So initially I started over here, then I got something like here, then most probably here. So what is happening? These are all elements of the set, and these are all upper bounds of the set. And then I have something here, which is intersection of ions. That means it belongs to the every set. It belongs to every set. If A is in the intersection of ion, A belongs to An and Bn. A is greater than equal to An, and An is less than equal to Bn. So this is the first understanding. What we claim, A is the supremum. So first, A is an upper bound, because if A is not an upper bound, then there must be an element of A. There must be an element of A which is strictly greater than A. But what is the problem if there is an element which is strictly greater than A? Observe this. First of all, A is greater than all the Ans, so B must be greater than all the Ans. B itself is an element, and BMs are upper bound. That means B has to be less than equal to BM. Meaning what? B lies between any AN and any BM. So in fact, it lies between AN and BN. So B must be in all of the ion. So B must be in the intersection. B lies in all the ions. B must be in the intersection. But B is not equal to A. That's a contradiction. Why? Because this intersection contains only A. So we have shown that there cannot be any B from A which is strictly greater than A. So that means it is an upper bound. Finally, I need to show that it is the least among the upper bound. Almost the same argument. If you have understood that, it is almost the same argument. So what I will take? I'll take anything less than A to be an upper bound. So if it is an upper bound, it has to be greater than the elements. But I already know A is less than equal to B, and so C is less than equal to B, and again the same argument. C is greater than AN. C is less than BN. So C lies in all of the ion. That means C must be in the intersection of the ion, but C is not equal to A. So contradiction. So that proves that A is a supremum or least upper bound. So what we have done, we have shown that completeness property of R can be replaced by nested interval theorem or nested interval property. So what property we have seen in terms of supremum in a bounded above set is equivalent to this nested interval property. So all these are in terms of sets. We'd like to connect it to sequence. Now the question comes, why should I think of sequence? Let's see. I have said in the beginning that the characterization property. Do you remember the characterization property? Characterization property of supremum. Huh? So what we say, if alpha is supremum of some set, then anything alpha minus epsilon is not an upper bound. It's not an upper bound. Okay, not an upper bound. If alpha is a supremum, it is the least upper bound. So anything less is not an upper bound. Meaning what? I should have an element here. Element of what? Element from A. Element from A. So now observe this. This is true for any alpha, right? So I can take alpha to be 1 by n. I just need alpha to be greater than 0. So for any natural number, 1 by n would serve the purpose, and I apply the same argument. What argument? That alpha minus 1 by n is not a supremum, because alpha is the supremum. So I must have some element coming from A, So what I have here? I have here the characteristic property of supremum that says that anything less than alpha would invite an element of A in this. This immediately says that alpha and alpha minus 1 by n has a distance 1 by n. So in this 1 by n distance, there is an element. So most probably distance between alpha and xn is not 1 by n, but less. See, this distance is less than 1 by n. So meaning what? If I try to write this, then what I get? Alpha minus xn or xn minus alpha is less than 1 by n. I believe we have encountered sequence. So this simply says that xn converges to alpha. Xn's are from where? From A. Xn's are from A, and it converges to alpha. So this simple characterization of is very practical, very useful. It immediately gives rise to a sequence in A that converges to super. So now I need to think that whether there's an if and only if condition. So I will not dwell on it right now, but for a bounded above set A, which has a supremum, I immediately have a sequence converging to it. Okay. So thus convergence sequence gives rise to some supremum. So that's something to ponder about. But anyway, I have established, or we have seen that in along with sets, we can talk about sequence also. So that's why I'm coming to sequence and try to see whether there is some sequential property or completeness property in terms of sequence. Okay, I'm running out of time. So sequence is nothing but a function. We denote it by xn, that's a standard. Our sequence will be real. Very important concept is subsequence. So when there is a sequence xn, we'll simply call x and k to be a subsequence. What? X and k, where nk itself is a subsequence of n, but nk is strictly increasing. So for example, if I have a sequence, simple sequence, say 1, 2, sequence n, what would be a subsequence? My subsequence can be 1, 3, 7, 9, 15, right? But this cannot be a subsequence because of this. The order has been missed. Okay, this is a simple way to explain. So when I have a sequence, in order to obtain a subsequence, I will simply collect terms of the sequence, but maintaining the order. The order has to be maintained. So if it is xn, if this is called xn, this is called xnk. Okay, nk precisely says about the position. So 3 is third position and so on. Fine. But this is very important that we understand what is a subsequence and how to construct a subsequence given a sequence. Convergence of sequence. So by convergence of sequence, we mean xn is a sequence and there exists some real number, and we say that given epsilon greater than 0, so we have some positive epsilon fixed. With this epsilon in mind, we say that this happens mod of xn minus x is less than epsilon when your n is greater than equal to some n naught. So for every epsilon, I should find some natural number and not such that after this natural number, all the terms of the sequence are epsilon close to x. Mod of xn minus x is less than epsilon whenever n is greater than equal to n naught. That's the idea of convergence. In that case, x is said to be a limit. We say xn converges to x. One can easily show that if limit exists, it is unique. Sequences are said to be bounded if all the terms are bounded. Convergent sequences are bounded. We are not going to show this. But bounded sequence may not converge. We most probably already are aware of this fact. For example, I can think of xn to be minus 1 to the power n. So I have a sequence which has only 1, minus 1, 1, minus 1, or minus 1, 1, minus 1, 1, minus 1, 1. This is a bounded sequence because mod of xn equals 1, but it does not converge. So bounded sequence may not converge. Of these sequences, one very important type of sequence is monotone sequence. Why monotone sequence, you might ask? But if you look closely in this picture, the way we have constructed the sequence xn, you can visualize that xn's are in fact coming closer and closer to alpha in a systematic manner or in only one direction. In other words, xn's are increasing. Okay. So one can always manipulate the sequence to make it non-increasing, but we can make xn so that xn increases depending on how I choose my 1 by n. So that's why it is important for us that in the characterization of supremum, we have obtained a sequence which converges to the supremum, and this xn is increasing. We call such sequence monotone sequence. So that's why it is important for us to understand what's monotone sequence. A monotone sequence is either increasing or decreasing. So when I say increasing, it may be equal also, and when I say decreasing, it may be equal also. If these are strict inequalities, then we would say that our monotone sequence are strictly increasing or strictly decreasing. Okay, I will skip this. This is a very interesting idea that every real sequence has a monotone subsequence. That's how important our monotone sequence are. Given any arbitrary real sequence, we can always manage to find a monotone subsequence. I will skip the proof. I believe the The slide should be available, so one can always go through it. What I'm interested is in the fact that if a monotone sequence is increasing, just imagine your sequence x1, x2, x3, x4, they are increasing. That means it is already bounded below, right? It's already bounded below. For example, if I have a monotone sequence xn given by n, 1, 2, 3, and so on, this is an increasing sequence. Since this is increasing sequence, it's already bounded below by 1. So a monotone sequence is already bounded below. Similar, monotonically increasing sequence. Similarly, a decreasing sequence is always bounded above. So now the question is, what happens if my monotone sequence is bounded? So we can plot sequence, right? So let's say I have a sequence which is increasing. So since the sequence is increasing, you can see that it's always bounded below. It's not going below this. But will it go up to infinity since it is increasing? Let's say it is bounded above. It will not cross this line. Meaning what? If it keeps on increasing, at some point, this increment has to stop. Stop means it will become very small. What I'm doing, I'm trying to see the increment, how it is increasing. If these increments are very small, why the increment is small? Because there are infinitely many terms, right? If all of they are keep on increasing at a finite scale, it will cross. I do not want this to cross. So if it is not crossing, that means the increment has to become very, very small. What do I mean by increment? That whether xn plus 1 minus xn, that difference, this increment. If this increment is small, that means if this increment is small, that means this most probably less than epsilon, most probably. So do I see a tendency of convergence? Most probably. That's the question we are interested in. Okay. So before answering the question, let's concentrate on this part, just this exercise that we have already seen. I have already shown you pictorially that if A is a non-empty bounded above subset of R, it will have a supremum. Then there exists a sequence Xn which converges to the sup. I'll leave it as an exercise, and one can show that this is increasing. So an increasing sequence which is bounded above by the supremum itself. So most probably, if a monotonic sequence is bounded, there is a tendency that will converge. So let's put it in a theorem. A monotone bounded sequence of real numbers converges. We'll call it MCT. So monotone means it may be monotonically increasing or monotonically decreasing. So I'll assume that it is monotonically increasing. So if it is increasing, it's bounded above. So I should have a supremum. Let's X be the supremum. And it is an obvious choice for us from this picture. From this picture, if this is a supremum that my sequence cannot go beyond this, then most probably this is the limit. Okay. So that's what I claim, Xn converges to X. That's a very simple idea. So first of all, observe that X is supremum, so X minus epsilon is no longer a lower upper bound. So I should have some element, right? That's a simple idea. Precisely the characterization of supremum. So this characterization allows me to construct an construct this Xn in such a way that, sorry, I have already Xn. I just want to show, not construct, this idea that xn, some xn would always be inside xn x minus a. That we have already seen pictorially. That means this, which simply means xn converges to x. That's the proof of MCT, because the other part follows immediately. If you consider xn is decreasing, you can consider minus xn is increasing, and the proof is immediate. So in both cases, monotone bounded sequence converges. That's MCT. We want to show that this sequential property is in fact equal to the set property, that nested interval property. Okay, so time won't permit me, so let's quickly go through whatever. It's almost the same idea that we have proved NIP. Do you remember? So to prove NIP, we'll start with the nested intervals. They are non-empty, closed and bounded. We want to show that intersection is non-empty. So these intervals are of these forms. And then for these ANs are increasing, BNs are decreasing. So by MCT, AN would converge to A, BN would converge to B. Which are these? From the previous result, I know these are supremum. So using again the fact that A is a supremum, BI is a upper bound, B is an infimum, AI is a lower bound, we have these criteria. So immediately we have A and B lies between AN and BN. And so AB are in each of the IN. So it is also in the intersection. Even if we do not consider B, then also we can show that A belongs to this intersection. So the intersection is non-empty. MCT implies NIP. NIP implies MCT. So what I have to show now, that if you consider a increasing sequence which is bounded above, an increasing sequence, monotonically increasing sequence which is bounded above, it has to converge. Idea, we have already encountered the idea. So this range of this sequence or xn's in the set, if I collect xn in the set, it's bounded, it's non-empty. So each time I will have an element of xn and an upper bound. So I'll construct I1 from x1 and y1, where x1 is the first element. It's actually a lower bound, but anyway, x1 is the first element, and y1 is any upper bound. Okay, y is an upper bound, so y1 is y. Remember the idea, making it half, then checking whether it's an upper bound. If it's not an upper bound, then there has to be an element greater than that. So we use the same idea to construct nested sequence. Why do I need nested sequence? Because I need to use NIP, nested interval property. So I need nested sequence of closed, bounded, non-empty intervals whose lengths are going to 0. Why? Because I'm making half each time. If length is 1, next time it is half, next time it is 1/4, next time it is 1/8. So it is going to 0. NIP says that their intersection should contain one single element. And I claim that our original sequence, the sequence we have started with, it should go to X. All you need to establish that Xn and X belongs to some IN. Remember, lengths of ions are decreasing. So if lengths of ions are decreasing, Xn and X are in IN, then distance of Xn and X is also decreasing. That's the idea, to show that this distance is going to 0. Okay, proofs are not difficult, almost the same. You just have to have a picture in your mind. You'll see it immediately. So what we have shown, in fact, we have shown that the completeness property in R, which we have shown in terms of, or we have defined in terms of supremum of a set, is equivalent to nested interval property, also monotone convergence theorem. There is, so I tried to say something about sequence and set, their connection. I'll simply skip this. Now the connection with respect to subsequence. Bolzano-Weierstrass theorem says that every bounded sequence R has a convergent subsequence. Okay. So it's basically a combination of statements. Every real sequence has a monotone subsequence. Thus, the bounded real sequence is a bounded monotone subsequence. But bounded monotone converges, so this subsequence must converge. So this relies on that any sequence has a monotone subsequence, which I have skipped, right? So please allow me just 1 minute, and most probably I'll give you some idea why any sequence has a. So let's say if my sequence is decreasing, then it anyway has a decreasing subsequence. The subsequence is the sequence itself. I may have an increasing. So then in both the cases, what I have, my sequence has a monotone, subsequence. This sequence itself is monotone, so the subsequence is sequence itself. Okay, let's assume that my sequence is not monotone. What do I mean by this? So I have a point here, I have a point here, I have a point here, then it again increases. It's not monotone, right? Then decreases, then again increases, then decreases. So it may be possible that my sequence follows some trend. What trend? It has certain peaks. What do I mean by peaks? By peaks, I mean that this value is greater than all the remaining values. So this value is greater than all the remaining values. Similarly, this value is greater than all the remaining values. This value is greater than all the remaining values. So I can construct a set containing such type of points, if possible, that I have certain kind of peaks which are decreasing in nature. So this will give me a decreasing subsequence, monotone subsequence. The situation can reverse. What do I mean by situation can reverse? So I can have this picture. So I have points here, points here, points here, points here. So remember, this sequence are not monotonically increasing, right? So it increases, decreases, increases, decreases, increases, decreases. So now what I have my peaks increasing order. Someone might question that what happens if this is not true or this is not true. You can mathematically show that if this is not true, then this will surely happen. Or if this is not true, then this will surely happen. After some stage, maybe. So this precisely say that given any real sequence, you will always have a monotone subsequence. What will have? Every real sequence will have a monotone subsequence. That's precisely what we have used. Every real sequence has a monotone subsequence. But my sequence is bounded. So that means my subsequence is bounded. But this subsequence is bounded monotone. MCT says that you have a bounded monotone sequence. It must converge. That means my subsequent converges. So what I have got, I've started with a bounded sequence. I have got it convergent subsequence. Okay, so this type of proof I do not like. For me, I always used to say that this is easy way out because I do not see what's happening inside. Okay, So I generally like to have some proof which construct. Can I construct a subsequence using whatever tool I have, simple possible tool? Yes, I can do that using NIP, but we'll skip it because we have to travel. We have to travel a bit, so I'll skip this. It can be proved using NIP. It's not difficult. But using MCT also, BWT, Bolzano-Weierstrass theorem can be proved. It's slightly difficult because it is not intuitive. In the other proof, I can show you something by picture. Geometrically, we can have an elegant proof. But this one, I cannot, at least I cannot show it to you geometrically. Okay, you have to go through such a proof a couple of times to understand what's happening over here. Unfortunately, I'll be skipping this one. So basically, we have proved BWT in terms of MCT, monotone convergence theorem, nested interval theorem. And in this process, we are trying to connect set, sequence, subsequence, and we are trying to show that it is sufficient to use either set or sequence or subsequence of a sequence for the completeness property of R. Okay, that's the last topic, because many a times you will hear that Cauchy property is the completeness property. So I cannot skip this. Please allow me 5 minutes. I'll try to complete. So by Cauchy, I mean that a Cauchy sequence, after some stage, all the terms are very close to each other. Okay, so so my board looks pretty bad. So if I have sequence going somewhere, let's assume that they are going in a forward motion. Okay, I can have all possible sequences, but eventually they are keeping distances. Okay, they are keeping distances. But Cauchy sequence means after some time they have to accumulate. Okay, as if they are purposefully moving somewhere. So all the terms would be very close to each other. So that's the property of Cauchy. It does not tell me that it is going to a specific place, that it has a limit. I don't know that yet. But it simply says that all the terms of the sequence are very close to each other after some stage. How close? Give me any epsilon. I can show you that it is epsilon close. Okay, that's the idea of Cauchy sequence. That after some n, xn and xm would be less than epsilon for all such n. Every convergence sequence is Cauchy. Okay, you can immediately show that, because if I want to compare any two element, you just compare first with the limit, because I already know that sequence convergence means distance between xn and x is very small. So in order to compare the distance between xn and xm, I will compare the distance between xn and x, xm and x. And their distance is very small, so this distance as a whole is very small. Cauchy sequence is bounded. Again, as I have said, Cauchy sequence has this property that it accumulates. So if I pick epsilon to be 1, I can show that after some stage, every element will be at a distance less than 1. So pick one of the elements, fixed one of the element, XMC. Then you can show that by property of triangular inequality of modulus, that mod of xn is less than mod of xn plus 1. But this property is after some stage. What happened to the previous terms? All the previous terms are finite, because I am already know what happens after m. What left out? X1, x2 up to xn minus 1. I do not know about this. But apart from this, all xn's are bounded. So previous finitely many, I'll simply look for the maximum of them and maximum of this number as well. This will give me the bound for Cauchy sequence. Okay. Another property that Cauchy sequence with a convergence subsequence convergence. So if I want to show Cauchy sequence convergence, all I have to find a convergence subsequence. Again, the idea roughly same, that I want to show if xn is a Cauchy sequence, then I need to find a limit, but I already know it has a convergence subsequence. So I have a limit of that subsequence. And this distance can be made small because this subsequence already converges. So this distance is less. And due to Cauchy property, I can choose nk sufficiently large that this would be close enough. So I'm sorry if I'm being hasty. Finally, this is our final where we want to land. We want to show that Cauchy sequence is convergent, and in fact, it is an equivalent property. It's just a combination of several statements. Precisely, Cauchy sequence is bounded. Every bounded sequence is a convergent subsequence. Then Cauchy sequence with convergent subsequence is convergent. So if we combine all the previous results like this, we get Cauchy sequence convergence. But again, this is not intuitively enough for me. One can always refer to Professor Kumarson's book on real analysis for an alternate proof, which I like very much. But since the proof is available in the book, and time is almost over, most probably it's over, so I will skip the proof. Okay. So our final goal, that all the statement that we have made in terms of supremum, in terms of sequence, monotone sequence, in terms of nested interval theorem, in terms of subsequence, in terms of Cauchy sequence, it basically results in the same. It basically tells us some specific property of R, and each one of them is equivalent to each other. So one of them can be chosen as an axiom, and all the others can be proved. But in order to do that, I have to show that it implies MCT. So I need to show that MCT is true by means of Cauchy criteria. So if you allow me quickly, Xn is monotonically increasing bounded sequence. I want to show that Xn is Cauchy so that I can show that Xn converges. If Xn is not Cauchy, what is happening here? Xn is increasing. So let me give you a quick picture again. So this is my sequence increasing. This is an upper bound. If it is not Cauchy, meaning what? Difference between any two elements would be greater than a epsilon because it's not Cauchy. So I can find any 2 points somewhere whose difference is greater than epsilon. Then again, some points which is greater than epsilon. So if I start from here also and say that next somewhere there is an element whose distance from this is greater than epsilon, and there is another element whose distance is greater than epsilon. This way I can cover epsilon, 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 epsilon distance finitely. I'll skip. I'll move away. I will cross this bar, which is not allowed because it is supposed to be an upper bound. That's the whole idea. So what we said, that alpha is in, there's an upper bound, say alpha. And then I say that Xn is not Cauchy. If Xn is not Cauchy, then I may find some Mn whose distance is greater than epsilon. Okay, so I start with n not 1, then there had been n1 such that this distance is greater than epsilon. Then there had been n2 which is greater than n1 such that this two element has a distance greater than epsilon. Why these are possible? Because Xn is not Cauchy. I can always manage to find two terms at some stage which is greater than epsilon. So I'm picking my stages, and this means that the ultimate distance, if I travel by r times, it will be more than the supposed distance, because if I start at x1 and alpha is the supremum, I cannot cover more than this distance, but I have already covered this distance which is strictly greater than this. This means I have to have a number which is greater than the supremum, which is a contradiction. So finally, these are the references that I have used, and my concluding remark, let me just go back to this one. What we have achieved? We have achieved starting with the axiom that every upper boundedable non-empty subset of R has a supremum. We have observed that in fact there are many statements on intervals, sequence, subsequence, Cauchy sequences, that they are equivalent and each can be replaced as an axiom for completeness of R. So let's thank all of you for your kind attention.
If anyone has any questions, then please raise your hand and we'll call you in order.
So most probably I hurried so much that.
Mm.
Oh, good
Yes.
evening, sir. I have one question, one innocent question, I think. My question is, sir, R has, we assume that R has a least upper bound property, and we are doing so many things that NIP, Bolzano-Weierstrass, and monotone convergence theorem, and these equivalent things. But unfortunately, we are assuming this result that R has a least upper bound property or any one of it, say NIP or something. We are assuming one thing, and we assuming this result and using this strong result, we are proving so many result, and in mathematics so many results we proved using this result. So I think isn't this unfair to mathematics? We are using um, this least upper bound property, and we are proving this many result, and this is unfortunately axiom.
Okay, so your question is, it is unfortunate that we have to assume something. But this is the basic of mathematics. You have to assume something to start with. Because you do not.
Yes, sir.
Okay. So if you do not assume, for example, when you take two real numbers, 1 and 2, say, you add 1 plus 2, and you get 3. And you claim that, okay, 3 is also, you do not claim, you basically assume that 3 is also a real number. So my point is, you have to assume something, the algebraic properties that we have assumed, the order properties that we have assumed, and that's completeness properties. One can in fact go this far to say that you start with an arbitrary set. You start with an arbitrary set. I don't know what that set is. And then say that it is a complete ordered field that I impose this condition. You'll get back your R or something equivalent to R. So without certain assumption, we cannot begin to do mathematics. What is R basically if you start with? So if you suddenly move with to an arbitrary set, let's say X is a non-empty set, right? And take non-empty set, and most probably it's not singleton. Even if it is singleton, okay, it's not singleton. So I have two distinct elements, x1 and x2. Say. Can I add them? x1 plus x2, does it make sense? If it does not make any sense, then I cannot do many things that we do in R. So I'm losing out, right? So I am losing many wonderful properties. I may have certain different angle of looking at X, but my point is you always need to assume something to work with, to begin with. If you do not assume, it means you can prove. Unfortunately, this completeness property cannot be proved based on field property and on order property. You have to assume something. You have to start at some point. You just remove completeness property and you will see that we cannot do many of the things. There will be many holes in our analysis. So we are forced in a way. Are you getting my point?
Okay, sir. Thank you, sir.
If there are
Yeah,
any
sir. I got it.
Sorry to interrupt. In fact, if anyone is interested, one can start with set theory itself. There are axiomatic approach of set theory, and even in set theory, means those are kind of abstract. So it tells us what are the basic things we need to construct and work on. So even in a very basic course of real analysis, in some books, you'll see just the field properties of R, and then they will derive all the other properties that we use on day-to-day basis in R. So that means I need at least those 9 properties to prove all the other properties. So they do not come freely. You have to assume something. Okay. Any other question, please?
Hello, sir. Am I audible?
Yes.
Sir, my name is Pratim Santra. I am going to ask, sir. We have seen that Cauchy sequence and regarding stuff to realize the rational number and integer. Okay, and as rational are dense in real, and there are also irrational which are also dense, but how can we construct the irrational number from our pre-existing knowledge of such convergent supremum and set upper bound sequence? Using those pre-existing knowledge, can we construct or can we approach the uh, irrational number usually?
Okay, so you want to construct irrational number just based on the fact that uh, using supremum, right?
Yes, yes. Till now, whatever you have covered or we are covered in the.
Okay, so you need to know the definition of rational. So anything that cannot be written as P by Q, right? So that would be irrational. So a very standard example or procedure you'll find in the book is the just imagine a set of positive real numbers. So set of
Yes,
positive real number whose square is less than 2 or less than equal to 2. X belongs to R. X is positive. X square is strictly less than 2. Can you?
yes, sir.
Okay. That's it. It is obvious that the set is non-empty. If I allow 0 to be there, x is greater than equal to 0, then 0 square is less than 2, 0 is there. 1
Yes,
square is less than 2, so 1 is there. So this set is not empty. This set is bounded above. You take x equals to 2, 2 square is 4, right?
oh,
So anything greater than 2 cannot be there. So 2 is an upper bound.
oh,
So you have a non-empty subset of R which is boundable. So now it should have a supremum.
yes, yes,
Now you try to show that that supremum is not rational.
yes.
Okay.
Okay, okay.
So that will tell us that there are numbers in R which are not rationals. It must be something else. We call them
Yes.
irrationals.
Okay, sir. Thank you, sir.
If there are no more questions, then maybe we can conclude. Yeah, so we thank you, Professor, for this interesting talk. It was really nice talk involving, and it even helped me as well to brush up my real analysis. I was out of touch. So, if possible, for whoever it is possible, please turn on your camera so that we can have a group photo. Jyoti, you can stop recording.